Okay, and welcome to an extra special edition of chemistry. We are going to discuss intermolecular forces. Okay. So the inter there is important. Intra equals within. Inter means between. Okay. So, like intramural sports meant competitions within, your school. Intermural sports would mean competition between schools. So, intramolecular forces would be chemical bonds. Intermolecular forces means between molecules. Okay. So, going back to the very end of the first semester, gases, you could ignore intermolecular forces because they are insignificant. The particles are really, really far apart. They're moving at very high speeds. So the intermolecular forces can just be ignored. For liquids and solids, you just can't do that. The liquids and solids are held together by intermolecular forces. Okay? It's just no longer... It just doesn't make any sense. It's a silly, facile, stupid notion to think you can ignore intermolecular forces. So we need to consider those intermolecular forces and what they are and their various strengths. So we'll go ahead and start with something we already know about, polar molecules, polar interactions. Okay, so let's just go with polarity to start with. Just a brief reminder, what is polarity? You have two atoms bound together. If they're of different elements, one will be more electronegative than the other. So you'll get something like hydrogen bound to chlorine. Chlorine is more electronegative than hydrogen, so chlorine will hog the electrons of that bond, the shared electrons in the bond. They'll spend more time over chlorine than on hydrogen, so chlorine will have a partial negative charge, hydrogen will have a partial positive charge. It'll have an overall dipole moment looking something like this, an arrow pointing toward the negative end of that bond. And if you have, multiple bonds in a molecule, then you have to consider the symmetry of the molecule. Is there broken symmetry? Will that lead to polarity? And in the end, a polar molecule is a lot like a magnet, only with electrical charge instead of magnetic. Okay. And then those magnets can associate with one another in solids or in liquids with opposite charges attracting, positive charges repelling. And so you can get structure. Oops. Just realized that I got some stuff backwards too far. So positive, negative, negative, positive. Okay, and so these polar molecules will interact with one another, and thus you get dipole-dipole interactions. Okay? A dipole is another word for a polar bond or molecule. So polar molecules like to interact with other polar molecules. They have these dipole-dipole interactions. On the same scale, you can get dipole-ion interactions. An ion is just like the extreme version of a polar bond, in that instead of just hogging the electrons, the more electronegative element steals them entirely. So you can get something like water molecules grouped around, say, a sodium ion. Okay, I don't want to draw all of them because that would take up space and time, but in this case, a water molecule is two hydrogens bound to an oxygen. Oxygen is more electronegative. Hydrogen is less electronegative, so you get partial positive and partial negative charges. So dipole-dipole and dipole-ion interactions, they'll go in the middle of a chart we're building here. So over here on the other end, to one end, you have weaker, generally speaking, interactions. And over here, you have stronger interactions. The stronger interactions are hydrogen bonds, or H bonds. A hydrogen bond is a specific kind of dipole-dipole interaction. So if you have hydrogen bound to oxygen, hydrogen bound to nitrogen, or hydrogen bound to fluorine, you can get hydrogen bonding. Notice that these are the three most electronegative elements in the periodic table. So what happens with hydrogen bonding is you get a particular kind of dipole-dipole interaction in which you get a very strong, significant interaction between the hydrogen of one of those molecules and the oxygen, in the case of water, of another molecule. And this here is your hydrogen bond. Hydrogen bonds are very, very strong compared to other non-bonding forces, or intermolecular forces. Excuse me, I should have introduced that term earlier. Another term for intermolecular forces is non-bonding forces or non-bonding interactions. So a hydrogen bond is very strong. They can go up to 5% of the strength of a chemical bond. So 5%, that's not very strong compared to a chemical bond. It's very strong compared to your typical non-bonding interactions. Okay, so hydrogen bonds are kind of ridiculous. They are way out there in terms of strength. Now, the molecules on either end of the hydrogen bond don't have to be the same molecule. Okay? So you can have, for example, ethanol. You have a CH3 here, you have a CH2 there, and then you have an OH sticking off one end. This hydroxide, as it's known, or alcohol group, is capable of interacting with water. Okay? It can, give and receive those hydrogen bonds. Okay? So ethanol, that is to say, forms hydrogen bonds with water. So ethanol dissolves very, very easily in water. And so do ammonia and hydrofluoric acid. They dissolve in water very easily and for the exact same reason, because they are able to form hydrogen bonds. So that is another thing to keep in mind. The things, on either end of the hydrogen bonds don't even have to have, oops, I injured that the wrong way around, don't even have to have, the same sorts of elements. Okay, water can hydrogen bond with ammonia just as easily as with another water molecule. Okay, ammonia, launches and receives those hydrogen bonds, no problem. Hydrogen bonding is very significant. Okay? If you have this guy right here, it might look sort of familiar. Okay, what I'm drawing is DNA, that nice double helix. The rungs of the ladder in the middle, where I'm drawing tiny little circles now, those are held together by hydrogen bonds. Okay? So hydrogen bonding is very significant. Hydrogen bonds don't just show up in DNA, they also show up in proteins. They are very, very important throughout biology and biochemistry. I mentioned, I'm starting to run out of room, but I don't want to erase this particular screen, but I mentioned launching and receiving hydrogen bonds. So here we have water interacting with ether, diethyl ether, or ethyl ether, depending on the name. It can, interact with water, but it's a one-directional sort of interaction, because here you have oxygen, but it's not bound to a hydrogen. Okay, so it only has half of what you need for a hydrogen bond, so it can interact with water, but not as well as the ethanol down here at the bottom that I'm circling now. Okay. So I talk about it in terms of launching and receiving hydrogen bonds. Okay. If you only have half the partnership, you only get half the interaction. And in terms of that sort of, halfway interaction, the important guy is the oxygen, nitrogen, or fluorine. Hydrogen alone isn't enough to do it. Okay. So hydrogen bonds are stronger than typical non-bonding interactions, than typical dipole-dipole or dipole-ion interactions. They're very strong intermolecular forces. At the other end, you have London dispersion forces. Okay. Those are named after a person named London, not the city of London. London dispersion forces, they explain why nonpolar compounds also form liquids and solids. Okay, so say you have something that's nicely nonpolar. Let's just go with an atom of xenon. Okay, it's a noble gas. It doesn't like to bond or anything. An atom of xenon just has a whole bunch of electrons. Those electrons are flying around the atom randomly. They're ordinarily quite well distributed, so it's typically just a nonpolar atom. But sometimes you end up with, just at random, one side has more electrons than the other, so you just get this random temporary distribution of charge. So random temporary distribution of charge, meaning it's a random temporary dipole. And when you get something like that, it doesn't have to be xenon. It could also be a molecule of iodine. You can also get a distribution of electrons, there as well. Those would be, temporary charges, and they'd also be partial charges. Okay. And when that happens, a distribution of charges like that will cause nearby molecules or atoms to shift their electrons in response. Those electrostatic forces extend outward, and you get what's known as an induced dipole. So, in other words, that temporary fluctuation of charge pushes other molecules and atoms nearby to shift their electrons in response. Okay? So it induces dipoles all over the place. And thus, you get these temporary interactions between these nonpolar molecules. And the more electrons a molecule or atom has, the more significant these London dispersion forces become. London dispersion force, or LDF. Okay? More electrons, more significant force. And of course, more electrons means, bigger, heavier molecules. So those are the three kinds of forces. Your London dispersion forces, your dipole-dipole or dipole-ion interactions, and your hydrogen bonds. Now, generally speaking, all else being equal, London dispersion forces are the weakest interactions, and hydrogen bonds are the strongest interactions. That doesn't mean that London dispersion forces are insignificant, because, think about it, you have a lot of solid materials out there that are nonpolar, or liquid materials, or so on. Okay, so if you look at the periodic table, let me bring that up real quick. So you look here at the periodic table, you see you have, the gaseous compounds up here on the upper right, because they're small and they're nonpolar. Okay, these guys are all diatomic compounds. Then you come down here to bromine. Bromine is also nonpolar. It's a diatomic element, and it's a liquid. You come down one step further, iodine is a nonpolar diatomic element, and it's a solid. Okay? So chlorine has 34 electrons. One molecule, I should say, of chlorine has 34 electrons. Bromine has 70. It's a liquid. Iodine has 106. It's a solid. So those London dispersion forces, they may be weak compared to other intermolecular forces, but they're still significant. They still have to be considered. So in any given situation, you would actually have to put these compounds through various tests to find out what sorts of forces are the most significant at what time. But you can basically compare two polar molecules, and you can say, okay, these two, they're both polar. This one's bigger, so it's going to have, like over here, so you can compare different molecules or different compounds, okay? So H2O versus NH3. Well, they're both about the same size, 18 grams per mole. Molar mass is a really good way to compare these things because the heavier molecule is going to have more electrons versus 17 grams per mole. Okay, and they both form hydrogen bonds. So, I mean, these molecules are going to be very, very similar in terms of melting and boiling points. Okay, so melting and boiling points are just a good gauge of the strength of intermolecular forces, okay, because melting and boiling points are caused by intermolecular forces. So they're going to be about the same, is what I'm saying. I would give the edge to water as being, higher melting and boiling points, stronger forces. Just because it's a little bit heavier and oxygen is more electronegative than nitrogen. Okay. So you should expect, just based on that alone, that water is going to have higher melting and boiling points than ammonia, and that is what you see. Okay. If you look over here on the right, okay, my pointer might be hard to see, but here in the middle on the right-hand side, see the boiling point of ammonia is negative 28 degrees Fahrenheit. That's negative 33 Celsius. Its melting point is negative 108 or negative 77 Celsius. Okay, so it has a much lower, right? It's, those little differences can add up in a big way is what I'm... Similarly, you can compare, say, methane to octane. Okay. These are both non-polar compounds. Okay, they are nicely symmetrical in that way. And carbon and hydrogen have very close electronegativity, so those bonds have very low polarities. So these organic compounds, with just carbon and hydrogen, they're non-polar. Nevertheless, we can come up with a way of describing these, in terms of their melting and boiling points. And we can base that just on the molar mass. Okay, methane is going to be a lot lighter than octane. So methane is going to have a much, much lower melting and boiling point. And in fact, methane is a gas at room temperature, and octane is a liquid at room temperature. Okay. Just because of those London dispersion forces. But, once again, you can compare, say, octane to water. Octane has a lower melting and boiling point than water, even though octane is going to be, let's see, 8 times 12 is 96 plus 18 has a molar mass of 114 grams per mole, roughly, whereas water has a molar mass of just 18. Okay. So the polarity and hydrogen bonding of water is really, really significant compared to the London dispersion forces of, octane. So maybe that gives you some idea of the relative strengths of those non-bonding interactions. So to recap really, really quick, you have your London dispersion forces are weaker than just being polar, which is weaker than hydrogen bonding, which is the strongest kind of interaction. Okay, and that is it for intermolecular forces. You're going to have to keep these in mind a lot of the time when thinking about liquids and solids. So